Hey, welcome. Today, we're going to crack a secret code, one that kind of runs the world around us. It's all about possibility. We're talking about counting, but not just, 1, 2, 3. It's about really understanding choice itself.
I mean, have you ever really stopped to think about it? How many choices do you actually make when you're just ordering lunch or getting dressed in the morning? It turns out there's a really cool and powerful way to calculate all those possibilities, and that's exactly what we're going to dive into. Okay, so here's the game plan. We're going to kick things off with the absolute foundation, the multiplication rule. Then we'll get into the two big ones, permutations and combinations. And we'll wrap up by tackling a trickier but super common situation, how to count when you have identical items.
All right, first up, this is the bedrock of everything else we're going to talk about, the multiplication rule. It's simple, it's elegant, and it is incredibly powerful. This is literally where it all starts.
And the rule itself, it's just beautifully simple. Basically, if you have a bunch of choices to make one after the other, you just multiply the number of options you have at each step. That's it. That's the whole idea. Simple, right?
Okay, let's make this real. Picture this. You're at a restaurant looking at a combo meal. You've got 4 entrees to choose from, 3 sides and 2 desserts. Now, for every single entree you pick, you still get all 3 of those side choices. And for each of those pairings, you get 2 dessert choices. You can almost see the possibilities just branching out, can't you? So how many different meal combos can we actually make? Well, we just multiply. 4 times 3 times 2. And that gives us 24 unique possibilities. It's amazing how quickly just a few simple choices can totally explode into a huge number of options.
All right, you ready to add a layer of complexity? Let's do it. Next up, we have permutations, and this is what we use when the order of our choices is absolutely critical.
And this right here. This is the single most important question you have to ask yourself when you're trying to solve these kinds of problems. Does the order matter? Seriously, your answer to that one question tells you exactly which tool to pull out of the toolkit.
So, with a permutation, the arrangement is everything. The sequence is what counts. Think about things like computer passwords or lock combinations. PASS is obviously a very different password from SSAP. Or think about a race finish. The outcome, ABC, is completely different from CBA when you're handing out gold, silver, and bronze medals.
So let's stick with that race example. Say we have 10 runners, all competing for gold, silver, and bronze. How many different ways can that podium be filled? Well, if you use the permutation formula, you find out there are an incredible 720 different ways for those top 3 spots to be filled. Wow.
But what about the other side of that coin? What happens when the order is totally, completely irrelevant? Well, that's where combinations come into play. This is all about the group you form, not the order you pick them in.
You know, the perfect example here is pizza toppings. Think about it. If you order a pizza with pepperoni, mushrooms, and olives, does it matter one bit if you told the cashier mushrooms, olives, and pepperoni instead? No way! It's the exact same pizza. The group is all that matters. Same thing goes for forming a committee or, say, picking lottery numbers.
Okay, so let's run with that pizza idea. A pizza shop has 12 toppings available, and you want to choose 3. How many different pizzas can you possibly create? Well, since the order doesn't matter, we use the combination formula, and it turns out you can make 220 different 3-topping pizzas. Pretty cool, huh?
So this slide just lays it all out perfectly, side by side. On the left, you've got permutations, where order matters. Think rankings, codes, that sort of thing. On the right, combinations, where order does not matter. Think committees, groups, pizza toppings. This is it. This is the core distinction you've got to remember. Okay, time to level up. What happens when the items you're trying to arrange aren't all unique? What if you have duplicates? This is a really common curveball. But don't worry, there's a specific technique for handling it. So let's take the word statistics. Right away, you can see the challenge here. We've got multiple S's, multiple T's, and a couple of I's. Now, if we just treated all 10 letters as if they were unique, we would way overcount the possibilities, because swapping one S with another S doesn't actually create a new word, does it?
So the very first step is to just take inventory. We have 10 letters in total, sure, but inside that total, we have 3 S's, 3 T's, and 2 I's. We absolutely have to account for these repeats if we want to find the truly unique arrangements.
And to do that, we use a special formula, It basically starts with the total number of arrangements as if everything was unique, and then it divides out the duplicates for each of those repeated letters. And when we do that, we find there are a staggering 50,400 unique ways to arrange the letters in the word statistics. Isn't that wild?
So there you have it. That's your counting toolkit. You've got the multiplication rule for when you're making choices in a sequence. You've got permutations for when order is absolutely critical, combinations for when it's all about the group, and that special trick for handling repeats. You're all set.
So now you've got the fundamental tools to see the hidden mathematical structures that are, well, everywhere. Once you start looking for it, you'll see these problems of choice and arrangement all around you. So, now that you know the code, what possibilities are you going to count next?